Yes, Sahil.
Yes, sir.
Can you zoom a little bit this page, question page?
A little bit.
Can you zoom in
Okay,
that
one second.
question page? Actually, this is very small.
Yeah. So, like, is it not visible?
Uh, yeah, okay, that is fine now.
Yeah.
Yeah, Sahil, you can start.
Yeah. Okay. So, welcome to the week 5 programming question number 1. So, this week is based on DFS and BFS, which is a tree traversal algorithm, very useful in competitive programming questions and as well as data structures and algorithms. So, in the previous live session, I had explained the problem statement, but once again, we will go through this problem statement. So, what it says is there are N towns in India and M bidirectional railways. Road networks also exist between towns. There exists a bidirectional road between X and Y if and only if there is no railway between X and Y. So, if there is X and if there is Y, and if there is a railway between them, then it's okay. But if we don't have a railway between them, then we will have a road between them. So what does this mean? That between X and Y, we will either have a railway or we will either have a road which connects both X and Y. Next, the train and car leave town 1 at the same time. They both want to reach town N. Car can only travel through roads, obviously, and the train can only travel through railways. Okay, so what it says is, we're starting from 1, we want to reach N, and car starts from here, the train starts from here, and they both want to reach the destination N. Okay, so this is what it is all about. Next, in order to avoid accidents between car and the train, you need to make sure that both car and train don't arrive at a town X at the same time. Note that the car and train are not required to arrive at town N at the same time, but are allowed to do so. Okay, so what does this mean? So this means that if the car and train are starting from node 1, town 1, and destination is town N, then at some town X, to avoid accidents, both car and train cannot reach this town X simultaneously. Okay, so if car is reaching town X in 5 hours, then train cannot reach X in 5 hours. It should either take lesser number of hours or more number of hours, because we want to avoid accidents between them. But for the destination, this is not the constraint. That is, if the car and train can arrive at the destination at same time, so simultaneously they can arrive. So if the car takes 10 hours to arrive at the destination, the train can also take 10 hours to arrive at the destination. Okay, so this is something which needs to be kept in mind. Okay, so now traveling to a different town using one railway or one road always takes exactly 1 hour. What is the minimum number of hours needed for both vehicles to reach town N? Okay, so what do we have to calculate? So if, let's say, car takes 6 hours, which is the minimum time for car to reach N, and train takes 8 hours, which is the minimum time for train to reach N, then we have to print the maximum of the we have to print the maximum of 6 and 8, which is 8. Okay, so what is the question? What is the question asking is, we have to print the minimum of time taken by car, comma, minimum of time taken by train. Okay, so this is what we have to calculate. Okay, so I think you have understood the problem statement. It is quite simple. Now let's jump on to the input, how we are taking the input. So the first line of input takes 2 integers and an m. N is the number of towns and m is the number of bi-directional railways. Okay, And next M lines will contain two integers U and V, denoting the fact that there is a bi-directional railway between towns U and V. Okay. So input is like we will take N, we will take M, and for next M lines, we will take U and V. If U and V means there is a railway between U and V. And for all pairs which are not present, in the input, that means we don't have a railway joining U and V. Okay, so for those pairs, there will be a road. Okay, there will be a road joining those pairs. Okay, okay. So this is one thing you need to understand. Now constraints are quite simple. N is still 400, and the order of M is order of n square. That means order of M is order of 400 square, that which is equal to order of 16 into 10 power 4, which is order of 1.6 into 10 power 5, which means that order of 1.6 into 10 power 5. Obviously, if the time limit is given to be 1 second, that means 10 power 8 operations can be done. 10 power 8 operations can be done, and we have the order of M is 1.6 in power 5. That means we can always apply BFS or DFS here, because both these algorithms take order V plus E. Mostly both these take in worst case they take order of edges time complexity. Okay, so here the time complexity will be order of edges, which is M, which is equal to order of 1.6 in power 5, which is obviously very like under the constraint of 1 seconds. So we can apply BFS and DFS. Okay. So I think we have understood the input also. And what is the output? We have to just print a single integer denoting the minimum number of hours for both vehicles to reach town and the maximum of arrival time of the car in town. So as I told, maximum of time taken by car, comma minimum of time taken by train. First calculate the minimum time taken by car, calculate the minimum time taken by train, and take the maximum of these two, and that is what would be the answer. But let's say if it is impossible to reach the town N by car or by train, either of them, if for either of them it is impossible to reach, then we will print -1. Okay, so this is the thing. Now let's understand this sample input which has been given. So the input is as follows. We have 5, 5, 4, 2, 3, 5, 4, 5, 4, 2, 3, 5, 4, 5, 5, 1, 1, 2, 5, 1, 1, 2. This is the input. This means that N is equal to 5, M is equal to 5. That means there are 5 towns. 1, 2, 3, 4, 5. This is the starting point. 1 is the starting point. 5 is the destination town.
Sahil, there is one doubt in the chat.
Yeah, okay. Yeah, so like, can you please explain how you got the time complexity again? Right. So like we know that BFS and DFS, the worst case time complexity is order of edges. Obviously, some log factor also comes there, but worst case, you know that it is order of edges. Okay. So, and here the edges we have been given as n square, which is 400 square, which is equal to 1.6 into 10 power 5. So in this way, we got the time complexity. I think it is clear now. Yeah. So this is the starting point, and this is destination point. Okay, so now these are the edges. These are the railway edges. So 4 and 2, that means we have a railway between 4 and 2. There is a railway between 4 and 2. We have a railway network between 3 and 5. between 4 and 5, between 5 and 1, between 1 and 2. Okay. So this is the railway network which has been given. Now, as I had said, that if a pair is not given in the input, that means there is a road between those two pairs, between that pair. So there is a road between 2 and 3. So like, to not make it messy, I will not like mark the roads, but you should know that if I have not added an edge between any two pairs, that means there exists a road between them. Okay. So okay. So now let's calculate the minimum time taken. Minimum time taken by train. What is the minimum time taken by the train? So we see that there is a direct edge between the source, that is the starting point, and the destination. So only 1 hour will be taken by the train. So it is 1 hour. Okay. And if we see the minimum time taken by car through the road network will be, let's try to calculate that. So there is a road between, there is a road here, there is a road here, there is a road here. Okay, so there is a road here as well, and there is a road here as well. Okay, so what can we do? We can start from 1, we can go to 3, which is 1 hour. Then from 3 we can go to 2, which is 2 hours, and from 2 we can go to 5, which makes it 3 hours. So the minimum time taken by the car is 3 hours. So what will be our answer? Answer will be maximum of 1 comma 3 is equal to 3, and so this is our final answer. Okay, so this was all about the problem statement. We also understood the time complexity. We also understood how to like what is the input, what is the output, and we also understood the test case. So I think it is simple. What one must think is, do a DFS or a BFS for railway network and calculate the minimum time. Do BFS or BFS for road network and calculate the minimum time. And at last, take the maximum of these two. Right. So yes, this is the algorithm. We just run the BFS and DFS for the rail network. We just run the BFS and DFS for the road network, and we output the maximum of these two. But why to run DFS and BFS algorithms?
Sahil,
Twice.
there is one more doubt in the chat. Could you please?
Yeah, so like Jayant is saying that BFS works. Yes, yes, BFS will work. BFS or DFS, any of the algorithm will work. Yes, you're right. And can use different colors for train and car. Okay, so I think okay. So this is a road network. 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 So Mihir, I think now you'll be able to understand which is the road network and which is the rail network. So I request you to pay attention because it was quite simple, but okay. So yeah, so for road, we'll start from 1, we'll go to 3. From 3, we'll go to 2, and from 2, we'll go to 5. So it makes it 3 hours. Yeah. So I hope it makes sense now, Mihir. Could you please reply in the chat?
He's saying that the pace is a bit fast.
Yeah, okay. I'll try to go slow. Yeah, sure. So yeah, talking about the solution, we run a BFS DFS algorithm on the rail network. We run a BFS DFS algorithm on road network and print the maximum of these two. So that is our answer. But why do we need to run these algorithms twice? Is there a better way to do this question in lesser time? Because in this case, we are running the algorithms twice. Can we solve this question by only by doing BFS or DFS only once? So those who have joined the session, like, would anyone want to try by using only one BFS or DFS traversal? How can we solve this question?
Mihir, would you like to try?
Okay, so he's not. Just reply in the chat, Mihir. Like if you know the solution or you just want to try. We have to run the algorithm only once. Okay, so how will we do? So Bhani is saying run algo on the complete graph. Like, what do you mean by complete graph?
You can unmute and say.
Yeah. Okay, so like no one is responding. So I cannot wait much. Just a minute, okay. So Mir, I will give you 1 more minute because it is like extending the session. Okay, so like Jayant is saying that either we run. Okay, so like if we see the chat box, Mihir has answered the question. So the condition that the train and bus can't meet at one vertex except the final one. Okay, it's just crawling. If there is a railway, then the train can take it and wait in town. And if there is no such railway, then there is a road. The bus can take it and wait in town. And instead, there is nothing forbidding this. Okay, sure. So how can we solve this question by running BFS or DFS? Only once. So it is like, okay, if there is 1, 2, 3, 4, 5. There are 5 towns, and we have a railway between 1 and 5. Then obviously the minimum time taken by the train will be 1 hour, right? But let's say if we don't have a railway between 1 and 5, then we know that there is a road between 1 and 5. So the minimum time taken by the car will be 1 hour. Okay. So in both the cases, if there is a railway between 1 and 5, we know that the minimum time taken by train is 1. And if we don't have a railway, that means there is a road between 1 and 5. That means that the minimum time taken by a car is 1 hour. Okay. So every time we know that we either have to run the BFS or DFS algorithm on railway network or road network, right? So this was the trick. Like, just if you don't want to run the BFS or DFS algorithm twice, okay? So I hope everyone understands this thing. This was a simple observation. So many a times, if you are solving CP problems, observation is a key. Observation plays an important role. So yeah, let's jump on to the solution now.
There is one more doubt that edges are weighted. How would you solve this question?
So like there is no okay, if the edges are weighted, okay. So the concept here is that from starting from 1 and going to 2, we are taking only 1 hour. So if you're saying that from 1 to 2 it takes 3 hours, from 2 to 3 it takes 6 hours, from 3 to 5 it takes 9 hours, then for this, if you want to calculate the minimum time, then Dijkstra algorithm would work. But that is like the questions on Dijkstra algorithm is for week 7, is for the next week. So we'll not discuss that here. But yeah, Dijkstra algorithm is for that only. Yeah, so yeah, so I hope the code is visible to everyone. So what we are doing is we are taking n and m as input, okay, and now map int com vector int railway. This is a adjacency list, okay, this is adjacency list, and in this 2D vector we are storing the railway edges, railway network, okay, railway edges, okay. So I hope this is clear. And now for each edge, what we are doing, we are pushing back, we are like appending into the adjacency list, and we are calculating the, like we are making the railway network, okay. So this follow. Now, as I said, if there is a edge, railway edge from 1 to n, if there is an edge from 1 to n, then what we'll do, if there is an edge from 1 to n, if there is a railway network between 1 to n, that means the time taken by train is 1 hour, right? So we need not do a BFS or DFS traversal over the railway network, right? We will do a BFS or DFS traversal on the road network, okay, right? So I hope this makes sense. And now we will form the road network as well, okay. So this is the adjacency list for road. So here what we are doing, for each pair of edges, if you, for each u and v, if there doesn't exist a railway, that means there is a road between them. So we are in this way forming the road network, adjacency list for road. And now this is the like basic, we are running the BFS algorithm here. So I've solved this question using BFS. So this is the BFS algorithm. You all know that we use a queue in BFS. So what we are doing, okay, this is the queue. We take a visited array, we take a level array. Level is like we just from 1 to n. So how BFS works is, this is the node, we go to here, we go to here. If this is a graph, let's say, and it is a starting point, then we mark the level of this as 0, this has 1, this has 1, this has 2, this has 2, This has 2, this has 2, and this has 3. Well, we know that BFS goes on layer by layer, right? So this is the level. So the time taken to travel from this node to this node will be 3, because the level of this node from the starting point is 3. Okay? So level represents the distance of town n from town 1. Okay. Now in the queue, so we have 1, we have 2, we have 3, we have 4, we have 5. So we push the first town in the queue, and till the queue is not empty, what we will do, we'll pick the front element of the queue. We'll pick the front element of the queue and check its adjacency list. Adjacency list contains all the nodes to which this node is connected. Okay. So let's say 1 is connected to 2, 1 is connected to 3. Then the adjacency list looks like this. 1 is connected to 2 and 3. So we'll traverse to 2 and 3. And if 2 is not visited, then we'll push the node in the queue. So like everyone knows how to like do the BFS algorithm that is taught in the NPTEL lectures. So I'll not go to the detail, but yeah, this is the BFS thing. And finally, we calculate the level. This is okay. So let's say we're starting from 1. We have 2, we have 3, we have 4, we have 5. Okay. And this is the network. Let's say this is the network. So what we'll do, we assign the level of this town as 0. We assign. So what will be the level of this town? 1, right? Of this town, 1. Of this town, 1. And what will be the level of this town? Will be 2. Okay. So what is the time taken by car or by train to start from 1 and to reach 5? It is equal to the level of 5, which is equal to 2. Okay. So that is why we're calculating the level. And if level of n is equal to 0, that means we started at 1, but we are not able to reach n. Okay. That is why the level of n is 0. That means we're not able to reach the destination by the road. And as the question said, that if either by train or either by road, we're not able to reach this destination, then we will output -1. So we are doing that. Else we output the time taken by the car. Okay. So this is what it is all about. Okay. So this was the case when there is a railway network between the starting point and the destination. But let's say from 1 to n, we don't have a railway network. That means we have a road network. So the else part, what we will do the same thing, but for the railway network. Okay. We do the same thing for the railway network. So so basically what we have done, we are running the BFS algorithm only once. Okay, only once, either for the railway network or for the road network. And this way, like we're solving this question. So I hope everyone understands the approach. Mostly people would have like ran the algorithm twice, one for the road network and one for the railway network. That will also work, but like just in case you want to like grow in CP, observation is very important. You need to observe things, right? So this was a very good observation by Mihir, that from 1 to n, either we will have a railway network or we will have a road network. So no need to do a BFS traversal, right? So that is one thing which you guys need to keep in mind, that observation is very important. Okay. So I hope everyone understands the week 5 problem statement as well as the solution. Okay. So now let's jump on to understanding the problem statement for week 6. Yeah. So this is week 6 problem 2. So this week is based on Dijkstra. So yeah. So as one of you guys mentioned that what if we have 1, we have 2, we have 3, we have 4, and we have 5. These are 5 towns, and it takes 3 hours to go from 1 to 2. It takes 4 hours to go from 2 to 3. It takes 6 hours. It takes 7 hours. This takes 1 hour. This takes 2 hours. And in this case, how will we solve this problem? We cannot simply run a BFS directly. Okay. So in these type of cases, we use our master stroke, which is the Dijkstra algorithm, a very famous, a very beautiful algorithm. I hope you guys will learn this algorithm in week six lectures. So yeah, let's try to understand the problem statement. So again, this problem is simple. You are a bus route planner, a high responsibility. There are n bus stops numbered from 1 to n. So from 1 to n, there are n bus stops. Let's say 2, let's say 3, 4, 5, up to n minus 1, and then n. Okay. The bus starts at stop 1, and its destination is stop n. The government has given you the task to find the route which takes the minimum time for the bus to reach stop n, starting from stop 1. So the bus will start from 1 and wants to reach the destination n. And here, what we have is from 1 to 2, x time will be taken, from 2 to 3, y time will be taken, from 3 to n, z time will be taken. And in this way, in this network, you want to calculate the minimum time taken by the bus to reach n from 1. Okay, so you have to plan such a route such that the bus takes minimum time. Okay, so there's a question in the chat. Are there any generic guidelines on when to use DFS versus BFS? I presume all problems solvable using DFS can be solved using BFS, vice versa. However, are there any class of problems which are better addressed using BFS? You may respond to this query at a later point once you are okay. So I will explain this problem statement, then I'll come to your question. Yeah. So I hope everyone understood the problem statement. Now let's look at the input, how we are taking the input. So the input contains 2 integers, n and m, which is 5 and 6. That is, n is 5, m is 6. N represents the number of stops, m represents the number of roads between the first n stops. Okay. So n is the number of stops. Okay. So we have 1, we have 2, we have 3, we have 4, and we have 5. And m are the number of roads between them. Following m lines will contain 3 integers u, v, and w. U, v, w. U and v are the stops, and w is the time required to go from u to v, and also w is the time required to go from v to u. Obviously, there is a road between these two, and w is the time required for the bus to start from u to go to v, and vice versa, because this is a bi-directional road. Okay. Yeah. So I hope the input thing is also clear. Now talking about the constraints, n, which is the number of vertices, it is 1000 m. Order of m, which is the number of edges, is order of 1000. Okay, that means again we can apply Dijkstra algorithm, right? Because we all know the time complexity of Dijkstra, right? It uses a priority queue, as we know. Yeah. So understanding the output for each test case, print the minimum time required for the bus to reach stop n, starting from stop 1. Obviously, you start at stop 1, you reach at stop n. You print the minimum time taken. If you're not able to reach the stop n, you print -1. Simple. And understanding this example, n is 5, m is 6. So we have 1, we have 2, we have 3, we have 4, and we have 5. From 1 to 2, it takes 2 hours of time. From 2 to 5, it takes 5 hours of time. From 2 to 3, it takes 4 hours of time. For 1 to 4, it takes 1 hour of time. 3 to 4, it takes 3 hours of time. And from 3 to 5, it takes 1 hour of time. So what is the minimum time required? So one possible route is to start from, okay, sorry. 1 to 2 was 2, 1 to 4 was 1, 2 to 5 is there, 2 to 3 is there, 1 to 4 is there, 4 to 3 was 3, and 3 to 5 is 1. Okay, sorry. Okay, so 1, 2, 3, 4, 5, 1, 2, 3. Okay, we have 6 edges. Okay, so now one possible route is this. This route is one possible route, but the time taken is 2 plus 4 plus 1, which is equal to 7. Okay, another possible route is this to this. Okay, this to this. Again, this is the time taken by the bus will be 7. Another possible route, start from 1, go to 4, 4 to 3, and from 3 to 5. Now the time taken by this is 1 plus 3 plus 1, which is equal to 5. And if you like try to find all the possible routes, 5, this route takes the minimum time, and that is why 5 is the answer. Okay, so this is about the problem statement. So in short, the problem says that you are a bus planner, bus route planner. You have n stops from 1 to n. You want the bus to start from 1 to reach n in minimum number of time, and for every u and v, for every stop u and v, you have the time allocated between them. Okay, not for every u and v, but for some u and v, you have the time allocated between them. How much time it takes for the bus to start from u and to reach v. Okay, and vice versa. So, and you just have to calculate the minimum time required if the bus is able to reach n. If the bus is not able to reach n, just output -1. Okay, so I hope this is clear. This is a very standard Dijkstra algorithm. Just apply Dijkstra and you will be able to solve this question. Okay, so I hope everyone understands the problem statement. Now, coming back to Bhani Roy's question, that when to use BFS or DFS. So I think, as you said, most of the questions, 90, I guess every question can be solved by either using BFS or a DFS, because it is just a graph traversal, right? So the only difference between them is that BFS is like it goes on layer by layer. Okay, it goes on layer by layer. So that is how BFS works, and DFS is like it is a depth first search. You should go to depth, then it's a recursive solution, right? So I don't think I will have to think about some special cases where BFS works better than DFS, or DFS works better than BFS. But through my experience, through the type of questions which I have solved, I have mostly applied BFS because mostly applied DFS, sorry, because it's a recursion, right? You just need to just need to write very smaller number of lines, smaller lines of code, and you are done. Whereas in BFS, you need to make a queue, right? You need to make a queue. You need to do some stuff, right? So my personal preference is using DFS because this is a recursive algorithm. Okay, so but telling you about cases when BFS is more better than DFS or DFS is better than BFS, I think I will have to think of some of the cases. But right now, I don't think there is much of difference between them. You can use either. You can use any one of them which you're comfortable with. Yeah. So I hope.
Yes, Sahil. Sorry to interrupt. Can I add something in this question?
Yeah, sure.
Yeah. So Bhani, actually basic purpose of the BFS and DFS is the traversal of the nodes in the graph. Okay, both algorithm works in this manner. But in BFS algorithms, we traverse the node in different way, level by level, and BFS algorithm we traverse the node in the depth first manner. Okay, so some problems is where if we need to find out the shortest path from any particular node to another node in the terms of minimum number of edges in between. Okay, so we always prefer BFS algorithm. Okay, so DFS is also find out the connected information if any nodes is reachable or not from any other nodes. Same things BFS we can also find if any other nodes is reachable from any particular node or not. Another application from using the BFS DFS is we can also find out the cycles. Using DFS and BFS, we can also detect the cycles in the graph. So both we can use BFS and DFS for this cycle detection. Okay. So these are some basic application. If a graph have the if graph have no weights in the edges, or if graph have equal weights on the edges, so we can use BFS to find the shortest path. Okay, if the weights are different, then we have to use the different shortest path algorithms like Best algorithm, Bellman-Ford algorithm, these algorithms. Okay, so I hope the answer is clear. Okay. Yes, sir.
Yeah. Thank you, sir. Thank you, sir. Yeah, so like I'm done with my part. From here, Satyik will take on. Thank you. Thank you so much.
Thank you, Sahil. So now we're going to start with, okay, I'll just share my screen. All right. So I hope the screen is visible. And Sahil, if there are any questions, please just let me know.
Yeah, sure.
All right. Let's just start with the explanation to the programming week 5 programming assignment question number 2. So you have been given a matrix, a 2D matrix. This is a story. Okay. Yeah. So you're given a 2D matrix of size m into n, filled with integer values. Each integer value is representing a color of that cell or the pixel. And now the main question is that you will be given the coordinates of the pixel or the cell x comma y and a new color value. And what you have to do is that if, for example, so you have to like change the color of the given cell and all the adjacent same color cells with the new color. So let's just take this question through an example. The input has been given as of this form. So here we are given m and n, m equals to 4 and n equals to 4. This is the matrix of size 4 into 4. And now we are given the coordinates of the cell that we need to start changing and the new color value, that is 8. This is the new color, and we'll denote it by this, denoted by X or C. Yeah. Now, okay, X comma Y. In this matrix, you can see X equals to 1. So as it is said in the question that indexing is done from 0. So this is 0th row. This is the first row. And X equals to 1. So we'll look in this row, and Y equals to 2 is given. So this is the first column, second, this is 0th column, first column, and this is second column. So X comma Y, this is the cell. So the old color here given to us is 3. And now the question is saying that we need to start changing the color of the cell from 3 to the new color C, that is 8. Okay. So first we'll change the color of the cell to equals to 8. Right. And now the question is saying that we need to change the color of all the adjacent same color cells too in the matrix. So if you see adjacent cells to this X comma Y 1 comma 2 cell is this, right? These are the the adjacent cells are not the diagonal cells. The adjacent cells are just this 7, 3, 5, this 3 and this 7. Okay. And now it is saying that it should be same colored cells. Earlier the old color was 3. So the adjacent cells with the same with the old color are this 3 and this 3. So according to the question, we need to change the color of these cells also. So once we change the color of these cells from 3 to 8, Then we need to again look in the matrix. We'll look here. Here we'll see that we consider all the adjacent cells. Here the adjacent cells are one, this 5, and this 3. But now none of them are colored as the old color that was 3. None of them are colored 3 right now. So we don't need to do anything further from here. But if you look in this cell, here you will see all the adjacent cells. That is this 5, this 8, and this 3. And now you see that this 3 is the old color. So we have to change the color of this 3 to 8. Then again, we are going to repeat this process for this also. We'll look at the adjacent cells and we'll find that this color needs to change. We'll change it to 8. Then for this also, we'll repeat the same process and change the color of this 3 to 8. So in total, we are in this matrix, we have to change the color of these 6 cells from 3 to 8. Right. So yeah, this is the main part. This is the question, the explanation for the question. And if you want to consider one more example, I just take this also. You're given M and N, 5 and 6. This is the matrix. And this is the value of the coordinates of this cell. And this is the old color. This is the new color C. Okay. Now in the matrix, you need to look for X comma Y. That is, this is the 0th row, first row, second row, and this third row. So this row and column is second. That is 0, 1, 2. This is the column. So here, this is the cell from where we need to start looking. And the color of this cell, this is the old color. We'll just make the old color was 2. We'll just remember this and just start looking the adjacent cells for this. You'll find that you need to change this one. For this one, there are no adjacent colors with the color 2. You need to see this 2. For this 2, we'll see that this 2 needs to be changed. And for this 2, we'll see that this 2 needs to change, this 2, and then this 2. And you see that no more cells we can find adjacent to these cells that whose color need to be changed. So I hope the question is pretty much clear at this point. And okay, are there any questions till this point? Okay, so all right. Let's start with building or just coming up with an approach for this question. You also let's just first look at the constraints. The constraints given to us, there's a number of test cases. This is T, and the dimensions of the matrix M comma N are set to 50 cross 50 maximum size, and the coordinates, the constraints, and the color in the matrices are from a range from 1 to 10 power 5. Yeah, and the time limit as given is 1 second. So yeah, just remember that before starting to come up with an approach, or just starting to think of the solution, just also look at the constraints always. Okay, so yes. Now as you saw, what you can get an idea of this question, like the last question that we discussed was based on BFS. And just think in the direction of BFS only, because it is kind of similar to that. And BFS, what BFS would we apply here? How would we apply BFS here? We're given the coordinates of X comma Y. We get this cell. And what we are doing is we're looking the adjacent cells of this cell. And once we find a color, the old color, anywhere in in these adjacent cells, we change the color to C. And then we look over these adjacent cells. Now we have to then look at these adjacent cells, and then we continue this process again and again. So what is happening is like, what you can do is you can come up with a queue, right? And you can start with X comma Y in the queue. Okay. And then you can start by, looking at the adjacent cells of X comma Y cell, right? Like here, X comma Y was this. And then you start looking the adjacent cells. Now, if X comma Y cell is given to us, what would be the adjacent cells of this cell? The adjacent cells would be X plus 1 comma Y, X minus 1 comma Y, X comma Y plus 1, and X comma Y minus 1. Right? It's pretty intuitive at this point. And so these are the cells we need to look at when we are at the X comma Y cell. And yeah, Mihir will come to that. So what we are doing is that, yeah, now we'll look at these cells and we'll check if the old color, like the color of this cell is denoted by maybe O as a variable. We'll look at the color of these cells. And if the color of these cells are equal to the old color, then this means we need to change the color of this cell to the new color C, right? So let's, for example, we found out that this cell, the color of this cell was O, that is the old color, and the color of this cell was O. So these are the two cells that we need to then look at. So in our queue, what we should do is then remove this X comma Y, because we have already looked at it, we have already visited it, change this color to C, and then push X plus 1 comma Y and X comma Y minus 1. Right. So these are the colors that we need to then change. These just right. For these cells, we need to change the color. So we have pushed in the queue these two cells, and we just then repeat the process. We look at X plus 1 comma Y, and for that we consider, okay, we'll check its adjacent cells, right? Now when we are considering its adjacent cells, we'll come across what would be the adjacent cells of this. It would be X plus 2 comma Y, X comma Y, X plus 1 comma Y plus 1, X plus 1 comma Y minus 1. And you'll see that X comma Y is repeated here. But when you check its color, it won't be O, because we have already changed to C. So that is why this is how we are keeping a track of the visited cells in our matrix, So that is how you'll consider these as cells, and then you will drop this coordinate and then move on to the next, drop this and push, and that is this is the algorithm that we're doing. And as Mihir mentioned, this is the flood fill algorithm. It is a famous algorithm, and this type of, you'll find many questions based on this type of problems. And this is a pretty approach to the flood fill algorithm. So let's just try run a case. Just consider this first test case only, where m equals to 4 and n equals to 4. And what we're doing is we're starting with X comma Y. So let's maintain our queue. And now what we're going to do is maintain our variable old that was given to us. When you look at X comma Y, you find it's 3. And our new color is 8 given to us. All right. So let's just first start with 1 comma 2, right, in our queue. This is our queue. And start with 1 comma 2. So we'll look at 1 comma 2. Just a second. Okay, look at 1 comma 2. That was this 3 over here. And now look at its adjacent cells. This cell, this cell, this cell. And you'll find that this is the old color cell. this color matches to that. So yeah, before looking at this, we need to change this color also. So we'll change this color to 8. And now we'll look at the adjacent cells. Okay, these are the two adjacent cells, and the color of these cells is equal to 3. So that is why we will push that into the queue. That is 1, 1 and 1, 3. And once we also changed the color of 1, 2 cell. So we need to pop this from the queue. And this is our updated queue at our first iteration. At our first iteration, this is our queue. Now, let's look at the next different element, that is the top element of this queue, that is 1, 1. This 3. This 3 we are looking at, this 3. We'll check its adjacent cells. Here we'll find that this is 8, this is 1, this is 1, this is 5. Okay. So there are no cells with the colors 3. Okay. So we don't need to push anything in our queue. And we'll just pop this from our queue and change the color of this cell to 8. Right. And we'll find that no adjacent cells are color 3. So we don't need to push anything in our queue. Okay. Next, we look at the front element of the queue, that is 1, 3. This is the element that we're looking at. We'll change its color to 8. And then look at its adjacent cells. That is this 5. This was 3, now this is 8. And this 3. Right? This is the old color, 3. So we need to push this cell into our queue. What is this cell? This is 2, 0th row, first row, second row, and the last column, that is 3. To be a push 2, 3. And then we also need to pop the front 1, 3 because we already looked at this cell. Right. And now let's look at the next element of our queue, the front element 2, 3. We look at 2, 3, change its color to 8. Pop this first from the queue. And now look at adjacent cells. This is 8, this is 5, this is 3. Again, we'll find the old color 3. We'll change, we have found the old color, so we need to push. We need to push. This is third row, third column into our queue. Right. Now let's again look at the queue. We still have one cell left over here, so we need to still look. Our BFS is not complete. Till our queue is not empty, our BFS isn't done. So we'll look at 3, 3. And 3, 3, this is change its color to 8. Pop this. And now let's look at adjacent cells. This is 8 and this is 3. We again find the old color. Push this. That is 3, 2 in our queue. Right. And then next move on to the next iteration. So okay, let's just mention this is our 0th iteration. This is our first iteration. At the second iteration, we are here, third iteration here. Okay. And now the last iteration, that is the 4th iteration. What we're doing is we're looking at 3, 2, change its color to 8, pop this element from the queue, and now look at its adjacent cells. Adjacent cells, we look at 5, 2, and this is 8. So at this point, we don't need to push anything on a queue because no adjacent cells are colored as the old color 3. And now you look at that the queue is empty right now. We have popped all the elements and we haven't pushed anything in this iteration. So our queue is empty. This means our BFS is complete. And this means we have got our new matrix. I hope this algorithm is clear. We have dry run on this case. And at this point, if anyone has questions, please feel free to ask. And we can then start looking over the code solution for this. All right, so I guess there aren't any doubts. Now, let's just look at the code solution. Okay, 1 more down. Okay, there's one question from me, that is, are there any theoretical limits? One second. Are there any theoretical limits to the accuracy or completeness of the flood fill algorithm? Okay. I'm not sure what you mean by theoretical limits, but if you so if you look here, what we are doing is are there any mathematical theoretical bounds in the ability of the algorithm to accurately and completely fill a given region in a 2D space? Okay, so if you see here, we have made a queue and we are running this algorithm till our queue is, there is element in that queue, right? As I explained, we have to run a BFS until our queue isn't empty. So as soon as our queue is empty, this means our BFS is complete. And this means our algorithm, our flood fill algorithm it has changed the whole, given that is whatever 2D space is given, we have changed it. So did I answer your question? Because, I hope this is clear. Okay. So, yeah. And okay, first let's just look at the complexity of this algorithm also. So here we're looking at particular cell and this adjacent cells. What could be the worst case? The worst case could be that we need to look at all the cells. Basically, all the cells are colored as O equals to 3. Then we need to look at all the cells of the matrix, right? So the number of cells in a matrix are m into n, right? And at each iteration, we are looking at only one cell. So the number of iterations that we need is order of m into n. So this is the time complexity of our algorithm, BFS algorithm. And now, yes, so let's move on to the code solution. Yeah. So, yeah. This is the part where we're taking the inputs for our matrix, for our m comma n, and this is our matrix. And we're taking the inputs for the matrix, then we're taking for the x comma x, y, c input. Next, what we are doing is we are building a new matrix, result matrix. What is this? This is the new matrix for our final, this is our final new matrix. And what we are calling is a function flood fill, right? This is the main algorithm that we are calling to build this matrix, right? Now let's look at this function, flood fill function, that is the main algorithm of our question. There's one more doubt in the chat. Also, in this question, we used 4 connectivity as mentioned in the question. Yeah, 4 connectivity as is what we are looking at the adjacent cells. How does the choice of connectivity affect the accuracy and performance of the flood fill algorithm? Can you give examples where one connectivity type is better suited than the other? All right. Okay, so yeah, I hope you are asking like 4 connectivity versus 8 connectivity. Okay, so earlier in this question, we are looking at the 4 adjacent cells of a cell in the 4 directions of the cell. And I hope what you mean by 8 connectivity is that now we need to look at 8 adjacent cells of the cell. What you're saying is that we given this, what you're trying to do is change the question. Okay, what you're doing is looking at, when we are looking at this cell, what you mean we need to, if we're looking at the adjacent cells, what you mean is like you need to look at this 5, this 7, this 1, this 3, this 5. Okay, these 8 cells you're looking at. Okay, so yeah, the question then changes a bit, but the main crux remains the same, that we still need to apply BFS on this question, right? Earlier we are pushing, we're checking the adjacent, just 4 adjacent cells. Now we're checking the 8 adjacent cells. Okay, still applying BFS. Obviously the iterations would be less because we're looking at 8 adjacent cells, and right, still apply BFS over there, and still the flood connectivity will flood fill algorithm will give us the answer, flood fill algorithm will remain the same. Just that we need to look at 8 adjacent cells instead of 4 adjacent cells. I hope this is clear. Okay, right. Now, yeah, back to the code solution. I'll explain this and then you can ask, later you can ask the doubts. Yeah, so where we were here building our final matrix and calling this fill function. First, we are maintaining a variable old color. For the old color, that is, look at x comma y that was given to us, cell, and maintain the old color. This would be easier and checking the condition, okay, later on. So, and then we are maintaining for m and n the dimensions of the matrix. Now, this is our Q for BFS, okay. And starting, this is our 0th iteration. At the 0th iteration, what we are doing is, as you remember, we are pushing x comma y into the Q. And this is where our BFS starts. So, yeah, while Q is not empty, as I said earlier, we have to run BFS until our Q isn't empty. And then at each iteration, what we are going to do is look at the front, that is the top, as we checked here, looking at the front of the Q and maintaining that this is the current pixel or the current cell and pop it from the Q. Okay. And now, also maintain the x comma y or the I comma j row and column of the current pixel. And now we need to check the 4 adjacent cells. But before we check the 4 adjacent cells, we also need to check, if we are either we are going out of bounds, or we are still, what you are doing is, you're doing I comma j plus 1. J plus 1 could be out of bounds. So first check this condition always. Otherwise you'll get an error. So, and now we'll check, check if the current pixel, the color of the color pixel has been colored or not. And if I comma j is, the color of I comma j is old color and the color hasn't been changed to the new color, right? We'll replace the old color with the new color, right? And then we'll push the adjacent pixels into the queue, right? We're pushing here and just changing and pushing. This is what we're doing in the queue. And finally, what it does is returns the final matrix of the final new matrix. The final matrix comes here, result, and then print it. And this is what we get. So this is the output that we're getting for the input cases, the 2 input cases that we considered. And if you look at the input 888 over here, right? So, yep, this was the code solution. I hope this was clear to everyone. Right. Are there any doubts still at this point? If not, then we can move on to the explanation for the week 6 programming assignment 1. Okay, so it seems there are no doubts. So, yep, let's look at the week 6 question 1. So what this question says is that you're living in a town with 8 houses, with 8 houses that are connected with our roads. And yep, such that no two roads connect the same pair of houses. So and the roads are bidirectional. That is, you can travel in both directions on the road. Also, there is a path between any 2 houses. What the statement means is that the whole network of the H houses and R roads is a one connected graph. If you see that this network would look like a graph to you, and this is one connected graph. It says because you can reach from any house to any other house, right? It says that there is always a path between any 2 houses. So this means our graph is connected. And the distance between two houses is defined as the smallest possible number of roads on a path connecting them, right? Let's just, to explain this statement, I'll just draw this. For example, this is right. So what, let's example, this was our graph it was looking at, and we need to find the distance between this houses 1 and 2. So according to this statement, what this statement says is that the distance between two houses is defined as the smallest possible number of roads on a path connecting them. So if you see, there are two paths possible. One is from here. And one from here, right? There are two paths possible. And so the distance between 1 and 2, in this path, the distance would be, there are 3 roads, 1, 2, 3. So the distance would be 3 here from this path. And from this path, there would be, this would be 1 and 2, right? So now the distance is defined as the smallest possible number of roads. The distance between 1 and 2 would be the minimum of all the paths, that is 3, 2, that is 2. So distance between 1 and 2 would be 2 in this case. So this is what this statement means. Okay. Now the main question starts over here. You live at a house number X. You live at house number X, and your best friend is living at house number Y. And what you have to do is that you love the scenery of the ride from your house to your friends. And now what the mayor of the town has decided, that he's going to build one new road. Only one new road has to be built in the town. A non-existing one. A new road has to be built between any two houses. And they have asked for your help to decide where to build that road. Right? You have to assign one road in your town, one new road, such that the distance between your house and your friends does not decrease. Right? So if you build a new road, the distance shouldn't decrease, the distance between your friend and your house. And now you have to answer the number of possible pairs of houses. Pairs of houses means like you have to answer the number of roads, number of new roads that you can build, such that the distance between your house and your friend's house does not decrease. Right? Let's look an example to understand better. So the first line of input. So yeah, in this input, this is H, this is R, this number of houses is 5, number of roads is 4, and you live at X equals to 1, and your friend lives as Y is equal to 3. And now this is the graph or the network that I've given. And let's just draw. It says that there is a road connecting 1 and 2, right? There's a road connecting 2 and 3. There's a road between 3 and 4. And there's another road between 4 and 5. It is a simple network. And if you see, it meets all the conditions that were mentioned in the first para. That is, the roads are bi-direction, you can travel in any direction. And there is a path between any two houses. The whole graph is connected, right? Now, we need to build a new road. We have to build a new connection between any two houses, such that the distance between X, that is 1, and 3, Y, that is 3, does not change. So earlier, the distance between X, Y, that is distance between 1, 3 was, there is only one path. The distance is the number of roads, 1, 2, 2. Now, you have to build a new road such that the distance does not become less than 2. It can be 2, but it shouldn't be less than 2. So what roads can you build, right? Let's look here. If you connect 1 and 3 with a new road, right? If you build this new road, what will happen is that when you calculate the distance between 1 and 3, it would come out to be 1, because from this path, it would be 1, and from this path, it would be 2. and the minimum of these is 1. And it is said that it shouldn't be less than 2. But now if we are connecting 1 and 3, it becomes 1. So this means we cannot build this road, right? So this is not an option. Okay. Now let's consider 1 and 4. If we connect 1 and 4, does the distance between 1 and 3 change? I don't think so, because from this path to 3, this distance would be 2, and from this path it is 2. The distance does not change, so this would be a correct road for us. So let's maintain a count 1. Okay, and now if we connect 1 and 5, the distance from this to 3 would be 3. This one road, this second road, this third road, right? And this 2, the minimum is still 2. So yeah, this is a valid road. So we'll increment our count. Okay. Let's build again our connection. Right. Now, if we join from 2, we see any road spec we can connect. From 2, 1 is already connected, 3 is already connected. 2 and 4 could be a possible road. Is this possible? Let's see. From this to 3, the distance is 2. And another part could be 1 to 2 to 4 to 3. This could be another path from 1 to 3. And the distance for this would be the number of roads that we're traveling is 1, 2, 3. 3, right? So the minimum is still 2. So we can connect this road, right? This is incremented. If we connect 2 and 5, we'll see that, yeah, we can build this road, right? And now what could be other part? If we connect 3 and 1 already seen, we cannot do that. If we connect 3 and 5, yeah, we can consider this one, because the distance between 1 and 3, there's only one path, that is 2. It doesn't change. So yeah, this is a valid road, and we increment to 5. And yeah, 4 to, we have considered all the cases right here. Okay, we have considered all of them. So our final answer would be 5. So the answer to this input case would be 5. I hope the question is clear. This is what you need to do. You need to find the number of possible pairs of houses, or the number of possible new roads that you can build, such that the distance between your house and your friends does not decrease. Was the answer 5? The answer was, yeah, the answer was 5. All right. So I hope this is clear. If there are any doubts, please feel free to question. All right. So, yep, this was the explanation for programming assignment, week 6, programming assignment 1. And yep, so this is clear to everyone. And yep, this is, thank you for joining the session.
Yeah, Jay. What's your doubt? Week 5, quiz 1. Quiz 1. Okay. Question number 2. Yeah, what's your doubt in this question?
Good evening, sir.
Yeah.
Sir, in the question, it is given that can DFS traversal be used to find the shortest path from source in terms of edges?
Mhm.
It is asking whether it is true or false. Like we have to choose it, sir.
So DFS or BFS?
DFS, sir. DFS.
Okay.
So, sir, it is possible, na, sir. Using DFS also we can find it, na, sir.
DFS using shortest path.
Yes, sir.
Okay, how you can find?
Sir, in BFS, what we will do is we just keep a visited vector so that we do not visit the vertex again, because because if you are reaching the vertex in BFS, that means that is the shortest path to it. But in case of DFS, in order to achieve the shortest path, we need to visit the vertex again, even if the vertex is visited, sir. That means we have to visit the vertex if it is reachable in shortest distance, then it was previously reached in some other distance.
Okay, okay. I think this query is also posted on the group, and we are looking into this.
Yes, sir. It was
Okay.
marked as a wrong answer, sir.
So we are looking into this. Yeah. If it is correct, so we will re-evaluate this.
Okay, sir. Thank you, sir.
Okay. Yeah. Yeah. Thanks, everyone. If you have any query, you can post on the group, Google group and Discord group. Okay. Thanks.
Thank you, sir.
Yeah.